Back to my channel where we dive deep into tech. I'm Sulaim Firdos and today I'm super excited to share the information about loading constant. So let's start. Why loading constant is required? ARM is a 32-bit CPU architecture where every instruction is 32-bit long. Any constant which are part of an instruction must be encoded within the 32 bits of the given instruction. And this naturally limits the range of constant that can be represented in one instruction. Most arithmetic and logic ARM instruction accept three parameters. They are destination, operand 1 and operand 2. The destination and operand 1 is always a register, and while the operand 2 can be a register, an immediate constant value, or a shifted register. Why is loading constant? What happens if you need a constant which cannot be expressed as an operand to immediate? You might have to notice that there is no ARM instruction to move 32-bit constant into register. Although we have different instructions in ARM such as move, but it is not possible to move 32-bit full constant from a register. Since ARM instructions are 32-bit in size, they obviously cannot specify a general 32-bit constant. So to move them, we need loading constants. How to load constants from the memory? To aid programming, there are two pseudo instructions. We will know what is pseudo instructions in later slides, but there are two pseudo instructions which we will use to move 32-bit value into a register. They are load register and the address, LDR and ADR. LDR loads constant pseudo instruction. ADR is load address pseudo instruction. How to load constant from the memory? The first pseudo instruction writes 32-bit constant to a register using whatever instructions are available. It defaults to a memory read if the constant cannot be encoded using other instructions. Steps to load a 32-bit constant into a register. First is immediate encoding or direct encoding. For small constant, if we have to move, if the constant is small, to fit directly into immediate field of the instruction, the assembler uses a single instruction to load the constant into the register. If there is a small constant, means only single instruction is enough to load the constant into the register. And this is typically done using an add immediate or similar instruction. We will add an immediate value. As here in example, we have added 42. Load immediate value 42 into the register name. Second, multiple instructions for large constant. We have to see for large constant also, right? So when large constant is there, what we do is when the constant is too large to fit in the immediate field of single instruction, the assembler uses multiple instructions to load the constant. This typically involves splitting the constant into high and low parts and loading them separately. So we split the constant here into two different parts, higher part and lower part, and they will be loaded separately. As in the example, here it is given. So the third is default to memory read. What if the constant is complex and even large? So if the constant is too complex to be loaded using the above method, that is the multiple instruction, if the constant is complex, then what the assembler is doing is the assembler defaults to the loading the constant from memory. This involves placing the constant in a known memory location and then using a load instruction to retrieve it. What here it does is, if the constant is too complex, then the assembler will default to loading the constant from memory. From memory only the constant is loaded. This will involve placing the constant in a known memory location. We will place the constant in a known memory location and then load it directly from the memory location. Then we use the load instruction to retrieve it. An example is given here. Moving on, the second pseudo instruction writes a relative address into a register. We are talking about pseudo instructions, so let us know what is pseudo instruction. Pseudo instructions are not actual machine instructions but are higher level instructions provided by an assembler to simplify the programming process. The assembler translates these pseudo instructions into one or more actual machine instructions. As it is written here, the pseudo instruction is a machine instruction, is not a machine instruction, but a higher level instruction. It provides an assembler to simplify the program. So, using these instructions will simplify the program. It is not normal instruction, it is a higher level instruction used to simplify the program. The assembler translates these pseudo instructions into more actual machine instruction. The assembler will translate these pseudo instructions to machine instructions later on. Now, as we know what is pseudo instructions, PC relative addressing. What is PC relative addressing means that the address used in the instruction is relative to the current value of the program counter PC. PC is program counter. The program counter holds the address of the current instruction being executed using PC relative addressing, allowing the code to be position independent, regardless of whether it is loaded into memory. This is useful in scenarios like shared libraries or dynamic loading for code. When dynamic loading is required, then these PC relative addressing will be helpful. So let us learn loading constant with an example. Here's an example of loading the constant. This example shows an LDR instruction. LDR instruction. We studied about two instructions, right? LDR and ADR. So this example will show about LDR instruction loading a 32-bit constant into register R0. This is a 32-bit constant. We will load that constant into register R0. So constant number DCD, this is a constant number. This example involves a memory access to load the constant, which can be expensive for time critical routines. Load pseudo instruction conversion. So pseudo instruction is here. Actual instruction is move R0 to immediate value we have given here. But the load instruction is load LDR R0 is equals to the constant. The second example is over here. Let us learn the same using MVN. MVN is also an instruction register. As you can see, there are alternatives to access memory, but they depend upon the constant you are trying to load. Compilers and assemblers use clever techniques to avoid loading a constant from memory. These tools have algorithms to find the optimal number of instructions required to generate a constant in a register and make extensive use of a barrel shifter. If the tool cannot generate the constant of this method, then it is loaded from the memory. The load pseudo instruction either inserts and move or MVN instruction. Load instruction, pseudo instruction will either use move or MVN instructions. And Here, in the second point, these tools have algorithms to find the optimal number. To find optimal number, these tools will have some algorithms written. We will use here barrel shifter. There will be a much more use of barrel shifter, and the tools cannot generate the constant by these methods. Then it is loaded from the memory. If even after using these tools it cannot generate the constant, then we will directly load it from the memory. To generate a value, if possible, or generates an LDR instruction with a PC relative address to read the constant from literal pool, a data area embedded within the code. Table above shows two pseudo conversions. The first conversion produces a simple move instruction. The second conversion produces a PC relative load. You use the pseudo instruction to load a constant to see how the assembler has handled a particular load constant. You can pass the output through a dissembler, which will list the instruction chosen by the tool to load the constant. Another useful pseudo instruction is a ADR. Let us talk about ADR instruction now, or address relative. This instruction places the address of the given label into register RD using a PC relative add or subtract. So here's a breakdown. ARM v5 extension. ARM v5 extensions are set of enhancements made to the ARM v5 architecture, which is part of the ARM family of processor. These extensions were introduced to improve the performance and efficiency of certain operations, especially in the context of digital signal processing (DSP) and multimedia applications. These ARM v5e extensions are made typically for digital signal processing and multimedia applications. Here's a breakdown of the ARM v5e extensions. First is Enhanced DSP instruction. ARM v5e introduced a set of DSP-specific instructions to accelerate operations commonly used in signal processing and multimedia application. These instructions can perform operations such as multiple accumulate (MAC), saturated arithmetic, and dual 16-bit arithmetic in a single instruction, which improves the performance of DSP algorithms. Second is saturated arithmetic. Saturated arithmetic prevents overflow by capping the results of a maximum value the data type can hold rather than wrap around. This is particularly useful in DSP applications where overall overflow can lead to significant errors in signal processing. Single instruction multiple data. ARM v5 introduces single instruction multiple data (SIMD) instructions for 16-bit and 8-bit data type, allowing the execution of the same operation on multiple data points simultaneously. This parallelism boosts performance in tasks such as image and audio processing. Fourth is Enhanced Load Store instruction. The extensions include enhanced load and store instructions that support operations on multiple data elements, improving memory throughput for DSP applications. That's it for today's video. I hope you found this information helpful and useful. If you did, make sure you give the video a thumbs up and don't forget to hit the subscribe button. Thank you.